You've probably heard this question before. For centuries, it was one of the biggest debates in all of physics. I mean, it seemed impossible for light to be both. It had to be one or the other, right? Well, a really clever experiment back in the 1920s didn't just pick a side. It gave us a stunning answer that completely reshaped modern science.
Okay, so picture this. It's the early 20th century, and physicists are feeling pretty good. They're pretty confident that light is a wave. And honestly, the classical theories worked beautifully for most things. But some new experiments using high-energy X-rays started showing something that the old physics just couldn't explain at all.
The setup itself was actually pretty simple. You take a beam of X-rays, its energy, its wavelength, all that good stuff, and you fire it at a target. In the original experiment, it was a block of graphite. The whole point was just to see what happened to the X-rays that bounced off or scattered from the material. And this is where things got weird. I mean, really weird. According to everything they knew about waves, an X-ray hitting an electron should just make it wiggle, and that wiggling electron should send out a new wave with the exact same energy and frequency. But that's not what the data showed, not even close. The X-rays that came out had a longer wavelength, which meant they had somehow lost energy. And that was the million-dollar question. Where did the energy go? It couldn't just vanish. That's like Physics 101, right? The law of conservation of energy says it has to go somewhere. But the classical wave theory? It had absolutely no answer. It was a complete puzzle.
And this is where our hero, the American physicist Arthur Holly Compton, enters the story in 1923. He looked at this baffling result and decided to bet on a radical idea, one that flew in the face of 100 years of physics.
Now, Einstein had already suggested that light came in these little energy packets for another purpose. But Compton took that idea and just ran with it. He asked, what if these packets don't just carry energy? What if they actually act like tiny physical objects when they crash into things? These packets, of course, are what we now call photons. But here's the absolute key to Compton's idea. He said these photons don't just have energy, they have momentum, just like a tiny little bowling ball. And that changes everything. Suddenly, you're not analyzing a wave anymore. You're analyzing a collision. This simple change in thinking reframed the whole problem. Forget about a wave gently washing over an atom. Compton said, no. Think of it like a game of pool. It's a direct, one-on-one collision between two little particles. And it plays out in three really simple steps. First, the approach. Your photon, the cue ball, comes zooming in on an electron that's just kind of sitting there. Then, step two. Bam! The collision. The photon smacks right into the electron, transferring some of its energy and momentum. And finally, the aftermath. The electron goes recoiling off in one direction, and the photon, now a little weaker, scatters away in another. And just like that, the mystery of the missing energy was solved. It wasn't missing at all. It was transferred to the electron, giving it the kinetic energy to get knocked out of the way. The particle model just worked. It explained everything where the wave model had totally failed. But, a cool idea is one thing. In physics, you have to show your work. You need cold, hard proof. And Compton? Oh, he brought the receipts. He backed up his whole billiard ball idea with some undeniable math. He worked out this exact formula. Now, don't let all the symbols scare you. All this really says is that you can predict exactly how much the photon's wavelength will change just by knowing the angle it bounces off at. Everything else here, Planck's constant, the mass of an electron, the speed of light, those are all numbers we already knew. It was a clear, testable prediction. This was the knockout blow. When Compton and his team actually ran the experiments, the results they measured lined up perfectly. Every single data point fit the formula. This wasn't just a theory anymore. It was the first concrete, verifiable proof that light really does act like a particle. And you can just imagine the shock waves this sent through the world of physics. It was a monumental discovery. So monumental, in fact, that for establishing this crazy dual wave-particle nature of light, Arthur Compton got the Nobel Prize in Physics just 4 years later, in 1927. So, okay, this is all fascinating history, but you might be wondering, why does this matter to me today? Well, it turns out this isn't just some dusty old theory. It's a fundamental principle that we use every single day in some pretty incredible technology.
I mean, just look at this list. The Compton effect is absolutely central to so many modern fields. We're talking about the radiobiology that makes radiation therapy possible, the tools we use to analyze materials, and even how we study the most extreme objects in the universe, like black holes.
Take radiation therapy for cancer, for example. Doctors use high-energy X-rays to target tumors. Well, how do those X-rays actually do their job? The main way is through Compton scattering. It's the primary way that X-ray energy gets deposited into tissue, both the cancer cells and the healthy ones. Understanding it is crucial for getting the dose just right. And get this, it even works in reverse. There's a process called inverse Compton scattering, where a super-fast electron can collide with a low-energy photon and give it a massive energy boost. Astronomers use this cosmic slingshot to understand the insane physics happening in the most violent places in the cosmos, like right around a supermassive black hole.
So when you step back, it's pretty amazing. A single, elegant experiment looking at some misbehaving X-rays completely changed our understanding of reality and proved the bizarre dual nature of light. And it really makes you wonder, doesn't it? What other fundamental truths about our universe are just hiding there in plain sight, waiting for the right experiment, their Compton moment, to bring them to light?